Okay, so let's start the class. Um, just to make sure I was clear last time. When for example you have a string here, so you're gonna drive oscillation. Okay, so you're gonna see there will be a wave that will move at a given speed, but the material here, so here you have a bead, it's not going to move with it. So the medium does not move. Only the disturbance is moving, only the energy is moving. You know that you're going to have energy because here it could be shaken, right? What I want you to see also is, so let's do it slowly, right? It's going to move at the speed, and then here it's going to be reflected. And what's happening here is that when the wave comes in, then it's going to be reflected. The reflected wave will interfere with the new coming wave. And because the wave can be at the same place at the same time, this is called interference. And what you get if you're shaking the string at the right frequency, you get what it's called a standing wave. That's how we make music with a guitar, harp, violin, right? So you are not shaking this way, but you are plucking the string and you are making a standing wave. And this is because of interference. Okay, so we'll get back to that. The other thing I want you to see is that it's shaking here, but the shaking is perpendicular to the direction of propagation. So this is called a transverse wave. It's when the oscillation here is perpendicular to the propagation direction. The direction of propagation, like an electromagnetic wave, works also the same way. And you see that little green bead here? It's not going anywhere. So this is transverse wave, because I know in the MCAT they have those conceptual questions, for example. And here someone asked a question. So you see this is air molecules, and you learn in chemistry, as long as it's not 0 Kelvin, so it's not the absolute temperature, they always have some kind of motion. They are moving, right? Because it's warm enough, and it's called a thermal motion. So nothing is happening there. Now I'm gonna make it slow. I'm gonna make a sound, so I'm gonna press here. Maybe slow is too slow. But what you should see is that first of all, the wave is moving, the disturbance is moving, and you see how the air molecules now are shaking back and forth, back and forth. But the air here, you see that little molecule, maybe it's oxygen. You have 20% oxygen, 80% nitrogen. That little molecule here, maybe it's nitrogen, it's not going anywhere, doesn't go there. It's only the energy that is moving. So a sound wave, okay, it's a longitudinal wave, because the shaking here, you see how those molecules are shaking? They are shaking in a direction parallel to the direction of propagation. So you have here all the air molecules are compressed, and here so here you have compression in that area here, and there you have an expansion, compression, expansion, compression, and so forth and so on. At the very end, you have your eardrum that will be pushed and pull at the same frequency. So that will send a signal to the brain, and your brain translates that as sound, which is very mysterious to me. But if I put that at a normal speed, that's what it looks like. The speed of sound is about 340 meters per second. 340 meters per second. So it means in 5 seconds, sound travels about 1 mile. 5 seconds, 1 mile. So it's so much slower than light. So when there is a thunderstorm outside, first you see the lightning and then you hear the sound. Because lightning is light, it goes so fast. So you see the lightning and then you hear the sound. By finding the lag in time, you can find how far away is the thunderstorm, so you know if you have to worry or not. So if you count 1, 2, 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi, between lightning and the sound, you know that the thunderstorm is 1 mile away and you don't have to be afraid. Okay? If you cannot do 1 Mississippi, then you have to do something. then maybe it's not that safe.
Or you supposed to like lie down. Best options.
When you have so many towers like here, I think you're fine because you have all these lightning rod. If you are in nature and it's all flat, like if you are in Belgium and you have thunderstorm, yes, maybe you have to crunch on the ground. You have to worry. So we talk about interference because a wave that happens because a wave, again, it's not like a building. It can be at the same place at the same time. So when they meet each other, they're gonna either reinforce each other, so that's called constructive interference, or they can destroy each other. That's destructive interference, right? So that's because of Thomas. That's because it's a wave. So you see, they can. So if you have two waves, they meet. They can either reinforce each other, or if you have a crest here meeting with a through, then they can kill each other out, and then they pass each other. So the big experiment we talked about was the Thomas Young experiment, the two slit experiment, right? We already talked about that so much last time. But of course, you have to do the experiment to understand how it works. But basically, you have two slits here. You have the laser. So it's like you have two sources now. The wave will interfere with each other. And I have put in my announcements, there is a great video by the channel Veritasium, I think it's called. So when they interfere constructively, so crest and crest, you can have a bright band. When they destroy each other, you have a dark band. So you have a series of dark and bright bands, right? And in the video I share, he bring a huge box, right, to a beach in California. He has a prism, not a prism. He has just a small two slit. He has two slit. Of course, it's a two slit experiment. So a big black box, all closed, two slit under the sun, and people they could watch those bright and dark bands, right? So if you really want to see what it looks like, watch the video. It's shared in my post. So you might ask, how come those bright bands are, they are not thin? Okay, they spread out. That's because of diffraction. Remember, each time light goes through an opening, it will bend around the opening. So it will spread out. So that's diffraction. So if for the pop quiz, I ask you what's the issue with resolution, it's because of diffraction. Right? You want to be able, the resolution will be the smallest distance you can tell things apart. And you can define resolution also for a microscope. And the resolution depends on two things, the wavelength and the size of the opening. So imagine the wavelength like a small particle. If it's very, very small, it goes through the opening, it's not going to feel anything. So the resolution will be very good. If you have a big opening, same thing, the wavelength is not going to feel so much the corner and you don't have so much diffraction. Does it make sense? So if you want to see viruses, if you want to see DNA, you cannot use visible light. So you cannot use a cheap microscope. You have to buy an electron microscope because turns out that electrons also behave like waves. They have wave properties and I don't know, I had a picture here. See, you have, so that's visible light going through two slits, and you have that pattern, but you can do the same thing with electrons. So electrons will behave also like a wave. So you're gonna also have series of band, bright and dark. So that was the Thomasian. So what else can we do with it? Interference. So this is the same thing. You have some math, but the math is just geometry. Is just to find out the location of the next bright band. So you have one bright band here and you have another bright band there. You can use geometry to find its location. So if you have a equation like that on the MCAT, it's just an equation. As long as you understand the concept, then everything else is math. So in physics, most important thing is to understand the concept. Then you do a drawing, you identify a physical quantity, and then everything else is algebra. Not even like algebra 2 at most, not even calculus, right? So we talked about that. There is one question today on the pop quiz. You see that if you do not hear any sound here, that's because the speakers are off by half a wavelength. So if they are off, shifted by half a wavelength, then you have a crest with a throw, crest here with a throw here, or valley. Then it cancel each other out and you're not going to hear any sound. So it's like a blind spot. If the speakers are off by a whole wavelength or two wavelength or three wavelength, then you have crest to crest and the sound is very loud. Okay, so we talked about that. And the last interesting thing about interference and applications, it's called the beats. So if you are in music, you know that phenomenon is that when you have two waves and you add them together, but they are just off frequency. Their frequency is a little bit off, so they do not have the same frequency. If you want to cancel out, like in this example here, we suppose both waves here to get that both waves here they have the same frequency because they come from the same audio system. But now if you have 340 hertz, for example, and here you have 341 hertz, what's going to happen when they combine together, and you can do the math, you get beats. And what beats sounds like?
Let me get these things so they're a little bit different in frequency. You can strike them both at the same time. Can you hear the throbbing? That is the result of interference, and the phenomenon is called beats. All right.
See, that only happens when there is a little shift in frequency. So this is called beats. And you can do that. If you add that sine wave plus this sine wave, you get that, which is nothing here, high here. So these are called beats here. You can have fun here and add wave, this wave plus that wave, you get this wave. Okay, and then standing waves. I want to talk about standing waves because it's about music. So when you have, and I show you that before, so let's go back to here, let's make it slow. So the wave, what's going to happen when I'm going to oscillate, like let's make a pulse to see what's happening. So you see, it's going to move, okay, it has a speed that depends on the tension, and then it's going to come back, it's going to be reflected, right? So it's hard to see because I have some friction here, but let's do no friction. So it's moving forward and then it's being reflected. You see that? And then it's going to be reflected again, right? So now look what's going to happen. I'm going to pulse. Look what's going to happen when you're going to have incident wave interfering with a reflected wave. If I'm hitting the right frequency, you're going to get what we call standing wave. So I'm going to try to do that. Look. I'm trying hard here. It's being reflected, and now we got standing wave. Standing wave, it's what we get when you are playing music. Isn't that cool? So let me show you. I have another. Can show you that. So you have two waves interfering with each other, and if you have the right frequency, they will be constructive or destructive. Okay, so let's start. It's going to be slow. Okay, so you're making a sine wave or just a wave. Okay, oh yes, it's a sine wave. So it's a driven system. Somewhere there, it's shaking the string. So nothing special there. You see, it has a given speed. There is no interference yet. When it hits the end, so it could be an end that does not move. Look. You see how it's interfering with itself? You see, the blue one is the reflected wave. The red one is the incident wave. And at the end, what you get a standing wave. And that happens only at given frequencies. We call that the resonance, right? And that's how we play music. So that could be a guitar, for example, that could be a violin, or that could be a harp. Okay, so this is also due to interference. I can make so that will be close and close, that could be a guitar. I can make I forgot the difference between a flute and a clarinet. I think that could be a clarinet. So the one hand is free to move, and it's also going to be reflected. So this is the one that comes incident wave. Then there will be one that is reflected. So you see here, that's your clarinet, because one hand is free to move, but I still get a standing wave. See how it works? So I have another harp here. So you have the green one coming in, the blue one being reflected. They're going to interfere with each other, and you have a standing wave. What does it mean, standing? It seems to not go anywhere. It's just not moving, right? It's going up and then down. These are called nodes, and these are anti-nodes here. Okay, so how do we relate that to music? Let me show you. I can have an harp. Can you see them? You see that? So depending on the tension in the string, you're going to have different speed. Okay, if you have a heavy chord, it's going to be more mass. So the speed will be less of the wave, but you have the standing waves here. So that's how the idea behind music. Okay, so you have the first harmonic, the second harmonic, the third harmonic, but that's the idea. Let me show you in a guitar. I don't know if I have a guitar. I think I have a violin. Let's look at the violin here. Here. Let's look at the first harmonic. So for the string, if you are playing a music instrument, you know that those strings here are not equivalent to each other. The mass matters, okay? They are thick or they are thin, right? So it will, depending on the mass, depending on how tight the string is, you have to adjust. It will make different speed. And once you have different speed, it will make different harmonics. right? So that's called the fundamental or the first harmonic, and it's a standing wave. What does it mean, the standing wave? It's an interference between a coming wave and a reflected wave. Okay, and then actually you never hear that with a violent. Okay, you will hear that with a tuning fork, for example. That will be very boring. Okay, if you have that sound. Actually, it's a mix of several harmonics, and that's what you will hear the white wave form, and it's a mix of all the harmonics. So the pitch is the frequency, but the timbre, that's what you hear. So you can tell apart a piano from a violin, for example, right? The fundamental is just the first harmonic, the first standing wave that you make. That's going to give you the pitch. So that's just the idea. Then you have also other instruments. So for example, if you have a flute is it open at both ends? I always forget the flute and the clarinet. Yeah, it's open at both ends, but you can still make waves interfere with each other. Except in that case, they are not waves on a string, they are sound waves, but they interfere with each other, and you see you get the first harmonic. Flute is pretty boring, right? I mean, that's the first thing you learn in middle school, right? The first music instrument that you play. And then you combine all the harmonics together. So here it's open, here and here it's open. So they are all standing waves, right? Now, if you have other instruments, so let's see, clarinet. Clarinet is closed at one end and open at the other end. So same thing as that kind of piano. You see, it's attached here, but here I can move. So that will be 1/4 of a wavelength. But it's a standing wave. Do you understand the idea? It's also due because of interference and resonance, because those here will vibrate only at given frequencies, not any frequency, one single frequency. This is 1/4 of the wavelength, okay? And it will vibrate only at a given frequency, otherwise it will destroy each other and nothing will happen. So I just have an example here. So sometimes you will do those. I did my organ pipe.
Okay, this is a demonstration of organ pipe.
No, but that's the same idea. Here I have that. So you see here you have a tuning fork. Okay, it's gonna sound one pitch, so one frequency. One tuning fork is one frequency. The sound wave, it's gonna be inside that tube, so it's open at one end, closed at the other end, and only for some size of the tube you will have resonance, right? You can make those standing waves. So this is resonance. You see, you have that standing wave, and then it goes down, and then you're going to have the second harmonic, the second standing wave. You see? So that will, oh my ear, so that will be a clarinet, for example. I have one video that I have recorded myself. I just looked for it. Can you see something that I will have made? Am I? Yeah, I am in the right frequency. Oh, this was me. Look at that when I was teaching lab. So that's 10 hertz, the first harmonic. You see, you have a string. So you see how it doesn't move, right? And then I'm going to increase the frequency twice the frequency. And now you're going to see two bumps. So that will be the second harmonic, and it's a standing wave. And it's very fun because if you pinch here, it doesn't move. So it's called a note. And then you go to 3 times the fundamental, so that will be the third harmonics. And look at that, 1, 2, 3. Okay, so that's the third standing waves. And then you go to multiply by 4. Multiply by 4 the first one, so 40 hertz. 1, 2, 3, 4. That will be the fourth harmonics. And each time you have a different frequency. This is 40 hertz. That's going to be 50 hertz. 1, 2, 3, 4, 5. Isn't that cool? And these are called notes. So if you pinch it, you're not going to feel anything, right? And these are anti-notes. So these harmonics, they have to do with resonance, right? You can, okay, another one that I saw. It's called the Ruben. Do you see something, Ruben? The one with fire interference bits. Oh, this one. It's called the Ruben tube. You see the standing waves? You can visualize them. So you see when he goes low frequency, you have less bump. Higher pitch, you have more bumps. So you visualize the standing waves. This is because inside the tube, you are making standing waves, which means some places the air is compressed, you have more oxygen, so more fire. And some places there is nothing, okay, so no compression, no expansion, so you have less fire because there is no oxygen. So you are making standing waves with the sound, and you compress the air or expand the air, and that's why you have more or less fire. So you increase the pitch, you see how many bumps you have? You have more bumps. Low pitch, you have more bumps. Isn't that cool? So for those who are in music, I will post that in Canvas if you are interested. Again, you can make standing waves with a string.
For this demonstration, I have my able assist direction and bound mode. It's the lowest
So first,
frequency
standing
mode.
wave.
It's called the first overtone. And this one,
Second
if you'll
one,
notice, is going twice as
but
fast
what I want you to see is
as
that
the
you have to
fundamental
shake
mode.
at the right frequency.
It
Otherwise,
has
you do not
a
get
node
anything.
that's
So
exactly
this is how
halfway
a
between Parker
guitar
and me.
or a violin
And that's a
works.
node where
String
there's
instruments.
approximately no motion going on.
So
And
if you go faster,
if I can get one of the higher nodes, I think that's 4.
so you see that he does not shake it at the right frequency, you will get nothing, right? This comes from the, I have the links in my Canvas. I like those, this website because he uses the same book as I told you to get, the Cutnell and Johnson. It's good if you are taking the MCAT. So let's talk about resonance. So what happened is that when you have a system that can oscillate, right, that is flexible, and you shake it, you drive it at the right frequency, we call that the resonance frequency, you can get very, very high amplitude. So you can get, hey, welcome back, you can get standing waves, right? So it's like when you are falling in love, for example, I call that resonance. You go off the roof, right? Or if you talk to someone to a very touchy topic that you're not supposed to talk about, boom, right? That person goes off the roof. This is also resonance. So the best example we always give students happened, I think it was after the war or during the war, I forgot, World War II, Washington State. So they just had built a new bridge, brand new bridge in Washington State in Tacoma. So it was called the Tacoma Bridge. And the engineer, I guess they skipped physics 2054 and they forgot about resonance. And here just when they opened the bridge, very strong wind was driving the bridge back and forth, like you are pushing someone on a swing, right? If you do it the right way, it's going to go higher and higher and higher. That's called resonance. And of course, you know what happened. So the frequency from the bridge was at the same frequency than the resonance frequency, the wind. The wind was pushing the bridge at its resonance frequency. And you see what happened? So that's a famous story. He forgot his dog in the car, so he went back to get it. Okay, he was not afraid. If I forget my gecko, I'm sure I will go back to it, right? And look what happened at the end. So he didn't die, and the dog was alive. So it's called the Tacoma Bridge, so very famous. So it turns out that, for example, if you have enough voice, if you have the right amplitude, and you sing at a single frequency, the resonance frequency of a glass, there has to be crystal. Sorry. Okay, you increase the frequency and you can break it, right? And there was a video from the Mythbuster, and they did it, and it's true. But you have to be able to really provide enough, hold it, and enough amplitude, right? Enough power. Boom. See that? So there is this amazing singer. I don't know if you know her because maybe you are too young, but she's the queen of jazz. Okay, a very famous singer. Her name is Ella Fitzgerald, of course, very famous, and they used her for a commercial for Memorex. So what was Memorex? It was back then when we didn't have the technology that we use today. They have magnetic tape. Okay, so you will have to record the voices or the sound on magnetic tape. And their point is that their Memorex, their magnetic tape is so good that you could record the voice of Ella Fitzgerald and still be able to break a glass. It's a very famous commercial. Let's read. No, we don't have sound anymore. Very famous. I think she was called the first lady of song. Okay, the queen of jazz.
Can the amplified voice of Ella Fitzgerald shatter this glass? Believe it. Ella Fitzgerald on Memorex cassette tape with MRX2 oxide. Can Memorex shatter the glass? Now we ask, is it mine? Or is it Memorex?
Okay, very, very famous. So if you are in marketing, very famous. And I mean, marketing students always study that. Memorex, is it live or is it Memorex, right? Because you cannot tell you cannot tell the difference. So very famous. I mean, the beautiful music. Okay, she's very famous. So resonance, for example, let's take another example. Okay, I have one which is very good. Let's say resonance. Okay, you're gonna help me to tell me what happened there. I think it's from Brazil. Very creative. So what happened? Yeah. Yes. No. We can, but you have to be able to have a lot of power, okay, in your voice. And so what they do, they take a crystal glass, they wet the finger and they go. So if you're a professional singer, you hear and then you reproduce the same pitch, and you should be able to break the glass. But not only you need to have the right pitch, but you need to have also the right amplitude. Very good, yes. But usually it's very high pitch. But you have to use crystal, and then. But you have to be a professional singer. So what happened here? How come she was not able to break the?
She couldn't match the resonance.
No. So, yeah, it could be that she doesn't match the resonance, but in that case, it's something else. So there is liquid inside, but it was sealed, okay, but that's not the reason. Let's say she has enough power in her voice. How come she was not able to break it? Yeah. Yes. Yeah, but that's too complicated. Something more simple than that. So they all break, right? Why do they break? Because glass can be broken, right? You try to stretch glass, it doesn't work, right? So what is it that cannot be broken? Plastic, right? Isn't that a smart commercial? So it's they made like a vodka. I don't know what's inside plastic, so that's why I thought that was very smart. Interestingly, also in earthquakes application. So how come you have some buildings that will collapse if you have an earthquake, and some building won't collapse? So it depends on the height of the building. Also, it's because they will react to only one frequency. So if the earthquake is producing a wave, I think they are called a surface wave, right? They are the most dangerous wave because they are the wave that move at the surface of the earth, and it has the right frequency, the same frequency as the building will break. Some buildings don't have that frequency, so they will not collapse. Isn't that interesting? So that's what he's showing
¿De
there.
acuerdo? Y el periodo está en función de dos cosas, de la rigidez del elemento, en este caso la solera, y de la masa. Este es un piso y esto es una columna. Entonces, los periodos varían en función de la masa. Este tiene otro periodo, este tiene otro
It's
periodo.
another frequency, right? They all have the same mass, but they don't have the same resonance
El
frequency.
periodo se altera, ¿de acuerdo? Este es una casa en
This
las
is a
lomas,
house.
que tiene un periodo muy cortito.
Oh,
Y
depends
estos
on the
son unos
frequency.
edificios que tienen más rigidez y uno de ellos tiene amortiguador. Si yo los excito, ¿de acuerdo? Este que tiene un amortiguamiento se para rápidamente y este sigue vibrando.
Está buenísima la explicación.
Entonces, si yo quiero tirar un edificio en la
So
colonia
here
Roma,
comes the earthquake.
¿de acuerdo? Lo excito con las aceleraciones de la colonia Roma, que son como 2 segundos. Entonces hago esto. Vean los
You see
edificios
how
que se
this
excitan
one
en la
doesn't
colonia
move,
Roma.
it doesn't
¿De acuerdo?
vibrate,
Los que coinciden
and this
con la
one
forma de
vibrates
moverse en
more.
el suelo. Las casas de la
So it depends on the resonance frequency. That's the idea.
Si yo quiero perjudicar a los ricos de las lomas, Lo hago con un periodo muy corto y hago esto.
So this one moves
Y
now.
los edificios altos no se afectan,
And the other
se
one
afectan los
are
edificios que
safe.
tienen periodos cortos. Esa es la idea,
You see
esa
how
es la
it
dinámica
works?
de las estructuras. Entonces lo prudente es que los edificios no se muevan como el suelo.
So TikTok sometimes have good stuff, okay? Not only bad stuff. So here you have another tube, and that's also resonance. You see the standing wave, and they use the styrofoam. So it's a tube here. You are making standing waves at different frequency. Wow, wow, wow. Oh, yeah.
Something I don't know.
Yeah, a club. So you can visualize those standing waves also on TikTok. I have another one I wanted to show you. You can do that with tuning forks. So two tuning for 440 hertz. You see that? He only strikes this one, but this one has the same frequency. Okay, so it's resonance frequency, so it will also vibrate. You have to put a microphone. He stopped, and here you can hear that. Isn't that amazing? That's a resonance. Microphone. You see that? So that's resonance.
So is that the sound wave from one is transferred to the other, and then it
Exactly.
resonates, and then it also vibrates?
Yes, but only if they have the same frequency.
Same.
So you have different tuning fork. So it has to be it's a A for those who have a musical ear, which I don't. For 40 hertz, I think it's a A, right?
Could you not have like a recycling of like the sound wave if you had them like in a circuit and you hit one, wouldn't they all start to vibrate together?
Yeah, they will all vibrate together, like a spring.
Yeah.
That, by the way, it could be like this one.
Here I have, in this demonstration, 4 sets of rods of different
You mean
lengths.
transfer
And they're all
to each other?
connected
Yes,
by this
especially
steel
because
base.
tuning fork that
Now, the question
vibrate
is, if
like
I
this, so it's
pluck
not
this
spread out
large
in a 3
rod,
dimension, right?
how
So
will
they
the
can
other
transfer to
rods
each other.
respond? Will they all start to
Yes.
vibrate? Will the vibrations be different depending on the...
So you see, only that
As you can
that one
see,
pick
when
up
I pluck
the
this one, the
only
matching
this
rod
one, because they
starts to
have
vibrate,
matching
while the
resonance
rests remain
frequency.
steady.
They have a matching frequency
This
they
is
like to
because
vibrate with.
when I set this into oscillation and sent vibrations through the base of a certain frequency, the frequency of this rod, which was picked up by this rod since it has the same natural frequency as this one, and sent to vibrate. The rest of these rods have different natural frequencies, which are not equal to the frequencies of these rods, and therefore they do not vibrate.
Isn't that interesting? So a lot of demo you can do also in 2 dimension, right? You can have resonance. Okay, so let's move to the next. So then, if you want to, if you are interested by music, you can go, and here you have some math, some equations, but we don't have time for it. But once you understand the concept, when you see it with your eyes, always try to see a demo, then it's not that hard to understand. Okay? Yes. Yeah. I don't know if we can, if we vibrate. That I don't know. what I know, we have a psychological resonance frequency. Like you talked to someone about a few months ago about the vaccine, for example, just an example, some people will go off the roof for one reason or the other one. Okay, so that's a resonance frequency. When you fall in love, it's a resonance frequency. Now, can you vibrate? It's a good question. Like someone on a swing will have a resonance frequency because you have to push at the right frequency, so it's going to higher and higher and higher. Okay, I will look it up, and I find something interesting, I will post it. So someone share, I don't know if that person is here, but someone share something very interesting about the cancer, right? Nanoparticle. So for example, if you have nanotube, okay, it's carbon tube, okay, so it's a conductor, right? You have those conductor inside the tumor, God forbid, in your brain. And then you have a changing magnetic field, right? The changing magnetic field will induce a current in those nanotube, and it's supposed to destroy the tumor. But I think from my point of view, it looks better than chemo, because chemo for the brain tumor doesn't work that well. Like you have like a 1 year survival rate. So I share that article with you. Okay, geometrical optics. So as you might have guessed, my watch stopped in the 80s. That's why I have those pictures. One of my favorite songs. So I have demos, but I forgot the demos. So I apologize for that. So we have seen the wave properties of light. Now we're going to look at the optics, right? So the light can be refracted. So this is called refraction. And that happens because when light, remember, if I try to trick you for the final and I tell you, gamma rays, they have high frequency, high energy, so of course they have to move faster. You say, no, 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 no. All the waves in the electromagnetic spectrum, they all move at the same speed. If you increase the frequency, you have to decrease the wavelength, such as when you multiply them together, wavelength and frequency, you get to the same number, the speed of light, right? In vacuum, they all have the same speed. But in a piece of glass here, what's going to happen is that light will be refracted because light will slow down. And blue will slow down more than red, okay? Because they don't have the same wavelength. So refraction, I'm going to show you why, but it happens because light will slow down when it goes through a piece of glass. You all know that light can be reflected, and we have seen that light can be diffracted. So it means light moves like it's blind, and as soon as it's going to feel a corner, it will bend around the corner, right? So you see, instead of going a straight line here, it's going to bend around the corner. Thanks to the refraction phenomenon, we're going to be able to make lenses, right? So you have diverging lenses. That's the one I have. That's for people who cannot see far. So if I remove my glasses, you are all fuzzy here. I don't see anything. But if I look close, I can see. So I am short-sighted. So these are the expansive lenses, and they are called diverging lenses. And I will explain why you use those for my condition, being short-sighted. And then you have converging lenses that will be magnifying glass, and those are for people usually when we get older, everything gets stiffer, including the muscle in the eyes. So we cannot accommodate the same way that we used to. So now you need reading glasses, and they are just magnifying glasses. So those are very easy to make. You go to CVS, you buy them for a few dollars. They are very cheap. Those here are very expensive because you have to adjust the curvature here. That will be expensive to do. So I had, it's okay, I took a picture of my demo and I will make a video at home of the demo. I just forgot. But you see, when you have a piece of glass here, light, and that's just red light, okay? That's why you don't have a rainbow. Red light will go and it will bend here, okay? It will be refracted. It doesn't go in a straight line. And then it will be refracted again when it leaves the piece of glass. So why is it doing that? Because as it gets inside the glass, it's going to slow down. So let me explain. Like, for example, here, imagine you have people holding hands. Can you imagine that or no? Right, that's one person, one person, one person, one person. You are looking with a drone. You have a drone and you're looking at those persons from the top, from above, and they're all holding hands and they walk on the pavement. So holding hands here like kids. You don't want to lose your kids, so you ask the kids to hold hands. And then all of a sudden, here you have grass or mud. So what's going to happen? This one is going to be slowing down because he's or she is walking in mud. So which one will go faster? That one, right? So do you see how they all bend, right? Does it make sense? So if you imagine, it's like marching bands. So they march, 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 march. This one is slowing down. So this one is still going fast. So it make a turn, right? So they turn in this direction. And that happens because light will move slower in glass, for example. So if this is glass or this is plastic, the light will move slower. So it will bend. So I have an app to show you. So this is refraction. And let me show you what it looks like. Refraction is called bending light. You see light move in a straight line in the vacuum when it enters some glass. It's glass. It will bend. And there is an equation, it's called Snell law, between that angle here and this angle there. It's a very simple equation. We're not going to look at the equation, we don't have time, but it's not hard to understand. So some part of the light will be refracted, some part of the light will be reflected. So let me ask you something. Is it red? Is it the same color here when it's refracted? This is red. What color is that? That's red. So it's the same color. Because it's the same color, it's going to be the same frequency. Okay, the color depends on the frequency. So this is red, so it's the same frequency. So if the speed goes down, but the frequency stays the same, what has to go down as well? The wavelength. Okay, let's see if it's true.
Color change.
So the color does not change. If you see if that sign over there it's red, coming toward us, it goes through the glass or the window, it's still red. So the frequency does not change. But the light, when it goes through the window's glass, okay, the wavelength will go down. So you see how you have smaller wavelength? So the distance between two crests, here is the wavelength. Here it gets smaller because the speed gets smaller. The amount by which the speed decreases, okay, it will be the speed of light divided by what we call the index of refraction. So for glass, the index of refraction is 1.5. That means that the speed of light inside that material will be divided by 1.5. So the light slows down. Do you understand? And by the way, if you look here, if you do the marching band, no, no, try. So, going to take a risk problem, right? For the sake of standards. So you see here, you see how it moves, move. This one slows down, right? Because it's glass. But this one keeps going fast, so that's why. Understand how it works? So that's good. So you go from fast to slow. Now, something very interesting. So, what's the question to ask? If you go from fast to slow, can you go from slow to fast, right? And yes, because you can look inside the swimming pool, you can see the fishes. So light from the fish go from the water, which is slow, to the air, which is fast. So let's see. If I go from water, say, to air. So that's the fish here, right? And here I'm located there, so I can see the fish. But where do I see the fish? Here. So this is me looking at the swimming pool. I don't know why the swimming pool will be up and this is the air, but the image of the fish will be there, right? Well, don't worry about that. I'm going to get back to that. But look what's going to happen here. I should make no, it's fine. Look what's going to happen. Ooh, you see here, there is no problem. Light can escape. I go from slow to fast. Some of it is refracted, so it can escape the water or the glass. Some of it is reflected. Look what's going to happen here. Can the light escape? No, it's trapped inside. So this is called total reflection, and that only happens when you go from slow to fast. It doesn't happen when you want to go from fast to slow. So that means you will be, if someone is trying to look at you, you will be invisible in that case. Yeah. Oh. Okay, so I have the fish. I have the picture of your fish. Okay. I made that. Okay, so look at that. You have the fish, right? So you have the light from the fish. So you have some light of the fish will go in this direction, some light of the fish. You will have no problem if you look at the fish from above. But look at the light coming from the fish here. It's going to be refracted. It goes from slow to fast. From your point of view, because your eyes and your brain didn't take physics 2054, you think that the light, or your brain thinks that the light comes follow a straight line, you're gonna miss the fish because you're gonna see a virtual fish here. You're not going to see the actual position of the fish. You see that? So it's gonna be you're gonna yes, it's gonna be lower of what you see. So if you try to catch it, you're gonna miss it, right? And you miss the fish. But then when you get some practice, you know that you have to go a little bit further down and then you get the fish. So whatever you see the fish, you go a little bit further down. Right? So here we're going to see a ghost fish here. It's called a virtual image just above the real fish. So that's because of refraction. So you see here, when you look at that pen, it's inside the water. It seems that the pen is broken. That because of refraction. Because our brain, doesn't know to go this way. Okay, our brain thinks that the light comes from that direction. So your brain sees the fish here. So your brain is tricking you. So that's how we have all those optical illusions. That's what they use. So for example, here, the feet here, from the lady goes here, and then it will be refracted, but the image of the feet will be here. So she will look like she has very short legs, right? And you see that when you are in the ocean, like in August when it's crystal clear, you look at your feet, something is wrong. Okay, it's like your legs are shorter, and that's because of refraction, the bending light. So when you go from slow to fast, it's gonna be refracted toward. And when you go from fast to slow, it's going to be refracted in this direction. But when you go from slow to fast is going to be refracted away. Okay, so the best way to understand how it works is to play with this simulation. So to go back to the total reflection, we talked about that last time, but for example, in fiber optics, fiber optics, you see how you are trapping the light inside the fibers. So those fibers here are made of glass, and when you have a laser, it cannot escape. It's going to be trapped inside. So this is called total reflection. And that only happens when light goes from slow to fast. So here, no problem, it can escape. Okay, so if you are located here, you can see the source. But if it makes an angle, like if it goes through a threshold, then the light is trapped inside the material and cannot escape. So that's how optic fibers work. Okay, and why do we use them? Because you remember I told you the frequency of visible light is 10 to the 14 hertz. That means you can transport 10 to the 14 bits per second. So you have more information to be sent during the same time than radio waves.
Just correlate. You just correlated data to light.
No, the frequency.
Oh,
Like when you want to transfer information using a wave. So it could be radio wave or it could be visible light. You can transport more information with visible light than with radio wave because there is a higher frequency. So there is a rule that the frequency is about the number of bits, 0 and 1, you can send per unit second. So radio waves have a lower frequency, so you cannot send as many bits, 0 and 1. So that's why they are using optic fibers.
yes, upgrading.
Fibers, it's more expensive, but you send more data, so it's gonna go faster. Exactly.
Very expensive.
Yes. So another thing is that since you are in marine biology, I don't know if you know, but in the ocean, you have something called the sound channel. So it means here, the speed of sound here is faster because it's not as faster and because why? I forgot because why. Because the temperature is warmer, right? So here it's faster. Here it's faster because you have more pressure. So in between, it's gonna be slower. Okay, so slower wave in that part here inside the ocean, and that's called the sound channel. So it works like light, except it's sound. So here the sound will move faster because it's warmer water. Here the sound will move faster because it's more pressure from all the water. So here we have what it's called the sound channel. And that's how whales communicate with each other, because when they're going to make a sound, the sound does not spread out and the energy is not lost in 3 dimensions like we have learned with light. It's going to be trapped. right? So it cannot escape. So all this energy is being carried along over a very, very, very long distance. So if you have like a whale, I don't know, in in the Arctic, northern hemisphere, maybe you have a whale chilling out next to Brazil, they can talk to each other because the sound, is not dissipated. Isn't that cool? Right? So there is this book called Red October, and in the book, and there was a great movie called Red October, and in the book they talked how during, I think it was the Cold War, the submarine, they learned to travel inside the sound channel. So that means the enemy, they could not detect the submarine. And when the book was written, I think the CIA or whatever, they start to be worried that there was a leak, but there was no leak. It's just the person who wrote the book was very smart and figured it out, right? That the submarine, they like to travel in that sound channel so they are not hurt. Isn't that interesting?
But they travel sound to whales, or
Yeah, the same sound channel. Because I don't know. You are the one in marine biology, so you have to know. I don't know where is exactly the sound channel, but there is a sound channel. Because you can Google it. Where is the sound channel? Mhm.
at a certain depth.
But yes, exactly, at a certain depth. And I'm sure the depth will change, right? Because it depends on the temperature here and depends on the pressure there. But they can figure it out. Okay, so this is called trapped light. So, for example, here the whale can see the squid because the light carries its image, cannot escape, right? So it's going to bounce back. It's called total reflection. So then he can see the squid there. He can see also the airplane. Maybe he will freak out, right? It's weird. Now, can the airplane see the squid? No, because the light from the squid cannot escape, right? But they will be able to see the whale because you have the light wave coming from there and being reflected, so you can see the whale.
So is it because the light isn't like properly squid?
So it depends on the angle, the incident angle. So if you have a small incident angle, then the light can escape. And then once you hit like a specific, there's a equation for that, boom, it cannot escape. It's trapped inside. See that? So that's what makes a diamond so shiny. There was a very good movie called Blood Diamond, right? But by the way, when they because they exploit, they have slaves, right, to extract the diamond, and they use kids. By the way, we talk always about the electric car, but to have a electric car, you need to have lithium and cobalt. Where do they come from? Like, for example, you have cobalt. Cobalt is from Congo, I think, and they are using slaves, kids, to extract them. So I know it's not better. And lithium, I think they use Chile. In Chile, South America, so they have to use a lot of water, which is very bad for environment. So I don't know. I don't think that batteries are so environmental friendly. And then you have to recycle them, right? You have all this pollution. So anyway, that was a very good movie. So in a diamond, what makes them so special is that the light, okay, from outside, it's going to be trapped inside the diamond. So it's going to be reflected again and again and again. And when it's reflected so much, it's also going to be refracted when it comes out, and it can you can have like the rainbow. So you have pink diamond, blue diamond, you have beautiful diamond. And that's because in a diamond the index of refraction is so large, right? So it's very easy to trap the light inside. That's what makes a diamond so shiny. So if you want to make sure it's not a blood diamond, you can buy zirconium and nobody will tell the difference, right? Unless they have a special skill to analyze, but you don't tell the difference between a real diamond and zirconium. And at least they are not bloody. So it's called total reflection. Now, if you have white light, you see how blue light is more bent, it's more refracted than red light. So that's how you have the rainbow. And that's Newton figured it out. So yes, because of the wavelength. So the blue has a smaller wavelength than red. So the change in speed will not be the same. So it will not be refracted the same way. That's how you have the rainbow. And so let's go back to it's really in a nutshell. But once you understand the concept, it's not that hard. Let's look at the speed. You see the speed of light here is 75% the speed of light in air. So it means when light goes through a medium like glass or plastic, the light will slow down. In that case, by 25%. Here in air, it's about 100% the speed of light. Inside there, it's gonna be less. How much less? This is water, by the way. So it's gonna be the speed of light divided by 1.33. So it means it will be 75% the speed of light in water.
Yeah, basically change the speed.
No, that's a good question. The angle of incidence do not change the speed, but it changes the refracted angle. So if I go back to air, so let's go back to air here. And so you see here it goes a straight line. The speed is just 1c. If you go in water, you see the speed is less, 75% than there. What changes here is the angle. So it goes straight line. Here it's refracted, more refraction, more refraction, more refraction. But you see here you cannot trap. Light cannot be trapped when you go from fast to slow. It can be trapped only if you go from slow to fast. So here, so what I want to show you is that because you have refraction, then you have what is called a converging lens. Okay, you see how light will converge at one single point? That point is called the focal length. So this is called the magnifying glass. Okay, so that will be the reading glasses that are very cheap that you buy at the dollar stores. They are very cheap to make. You can buy them for $1. I mean, now it's not $1 with inflation, it's 1.25, right? 25% more. But that's a converging lens. You see that? Then here you have the opposite diverging lens. So these are the expansive one, the one that I have, okay? It's for people who are short-sighted, who cannot see far. So this is diverging. Isn't that cool? Right? Now, if I have white light, what can I do? I can do the rainbow. You see, that's a prism. It's white light, so it's not only just one frequency, it's all frequency mixed together. And when it goes through glass, now it's not going to be refracted by the same amount because the speed of light depends on the frequency. See how it works? Now, if I go back to my slides here, that's the that's the demo I wanted to show you, and I forgot it at home. But you see, so this is one frequency. You see how light is refracted? Now this is a converging lens, like a magnifying glass, and the light coming from very, very far away will focus at one point. And then you have a diverging lens. You see the light will diverge away, and it seems to come from a single point. Okay? See how it works? Now, just to want to, oh, by the way, for example, a mirage. How does a mirage works? So it's very hot. You are in the desert, and this is the sand, right? So because airs, you can think of air as made of layers, right? So here it's going to be very warm, and here it's going to be cooler. Light from the sun will be refracted. Okay, here you have a total reflection, and your brain thinks that the blue from the sky comes from a straight line. So your brain is going to see the sky here. So you think that you have water, you start to run, you are so happy, you jump, and there is nothing there, and you break your head. It's like when you are driving and it's very hot outside, it looks like you have water on the pavement, right? But of course it's not there. This is because of refraction.
Sometimes it even keeps moving.
Yes, yes. Why? Why is it moving? That's a good point. Why is it moving? Because the air is moving as well. That's why the star seems to twinkle, 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 little star, no, 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 no. That because the atmosphere comes into layers, right? And the layer move relative to each other. That's what make a star twinkle. I don't know if I have a video about twinkle of stars, but it's super cool. Yeah,
Hi
you
friends,
wrote the subject.
I'm sure the layers of the star are up glass at different temperature. The cooler layers are more dense compared to the warm layers. So the atmosphere is made up of many layers having different optical density. Now when we look up at the stars, the light is coming from the star. When light enters the atmosphere, it undergoes refraction because light is going from vacuum to the atmosphere. As we discussed, the atmosphere is made up of many layers having different densities. The bending of light also takes place at the boundaries of these layers. So the light from the star that reaches our eyes has gone through many refractions. If we trace back the light, the star is at a different position from its actual position. As you can see, the apparent position of the star is higher than its real position. And this takes place due to atmospheric refraction. But remember, the layers of the atmosphere are constantly shifting and changing. So the refraction of light is continuously changing and the apparent position of the star keeps fluctuating. The path of light coming from the star is constantly changing. And so the amount of light that enters our eyes keeps changing. As a result, the star appears brighter sometimes and sometimes dimmer to us. This bright dim effect makes us think that the star is twinkling.
Did you understand?
It's interesting to really think about the perspective. It's like the stars are looking at us as if we were looking at fish.
Yeah,
Because
yeah,
the
yeah,
superposition is not the
yeah.
same.
Exactly like this one. Look at that, right? So next time you want to catch a fish, you know where to try to catch it, right? So for example, if you have a fish here, it seems to be there, but actually it's here, right? And it depends if it's fresh water or if it's salt water, because the refraction won't be the same. Okay, so next time you want to catch something with a net, you have to go a little bit deeper. Okay, so there was a few, one more thing for the eyes. I want to get to the eyes. So this is called, so you see for example, in a pair of binocular, you don't use mirror because they can be mirror can be scratched very easily. You can use total reflection. See, you have a total reflection here, total reflection there. So you can have a total reflection inside here. That means it cannot escape the glass. During the Cold War, so I told you have a sound channel inside the ocean, so the waves, they can talk to each other. You also have a sound channel in the atmosphere, because here you have the ozone layer, so it's going to be faster for the sound to travel. Here it's going to be warm, and here it's going to be cool. So if there is a noise very, very far away, it can be reflected, and you are not losing the energy in 3 dimensions using the inverse square law. So during the Cold War, the Americans were spying on the Soviet Union, trying to find out if they were doing nuclear tests, right? The bomb, the hydrogen bomb, right? So they were listening to them, and the way they were listening to them was with the technology of the time. So there was a balloon, but the balloon was attached to a huge microphone, and the microphone at the time, they looked like saucers, right? That flat disc. One day, and then later on it was disclassified, but at the time it was very classified. One day the balloon crashes, the saucer fall down, and people saw it. They saw a saucer flying from the sky. So they thought, oh, you have a terrestrial life over there, right? Some maybe some alien are trying to invade us. And of course, the military were very, very, very happy about that, because they say, okay, like that, it stays secret. They wanted that to stay secret. So people thought they were seeing a UFO. And guess where that happened? In the US. Roswell. And then came the whole story about the Roswell alien. It was not an alien. They were just spying on the Soviet Union at the time. And that's a nice application of the sound channel, right? So it was classified for a very long time, and then it became disclassified, but nobody paid attention to it. So it's interesting story. So about the eyes. So okay, you have converging lens, diverging lens. You can have the same thing with mirrors. You have here, it's a concave mirror here, and it's a convex mirror there. So this is our eyes. Here we have the lens. Here it's like a converging lens. It works also with the liquid there, make things converging. So if you have a normal eye, if you look at something, for example, very, very, very far away, it's going to converge at the right place, where all I forgot what it's called here, it's not neuron, it's like cones. You have cones, right? And it's connected to the optical nerve and goes to your brain, everything is fine. However, if you have an eye like I do, so if you are short-sighted means that instead of having a nice spherical eye, your eye is more like an egg. It's squeezed, right? It looks like an ellipse here. It's like an egg. So then what's going to happen? My image is here, but there is no cone. So then the image here, you see the light rays will spread out, and the thing that I'm trying to look like very, very, very far away, it's going to be all fuzzy. Like you are all fuzzy if I do that. Okay, I'm not even kidding. Everything is fuzzy here. So what do we need? We need a diverging lens that will make the rays diverge a little bit. So now I can hit the cones, and now I can see. And why is it so expensive? Because you have to make the curve here just the right way. So it's a lot of curving lenses, and it's very expensive. So you can buy online $40 glasses, but sometimes they never fit. In my case, they never fit. So I always end up paying like hundreds of dollars for those lenses. That's how it works. Now, what's happening when you get old? When you get old, you are not able to squeeze, to adjust, right? So this lens that you have in your eyes, it can be adjusted with muscles here attached. Okay, so if you try to read something very close, your eyes can adjust because the muscle here can work. So the muscle can make the lens thicker, right, when you are trying to read something very close. As you get older, like, and I can testify, okay, I'm not lying to you, everything gets stiffer, okay, everything, including the muscles here. So that means you cannot read well. Okay, you cannot adjust as much as you could before. So now the image is it's missing. It's the opposite. The image will be there, and again you don't have cones. So you need to have those magnifying glasses here to bring back the image from here to the screen here, which is made of cones. Is that interesting? Now you have the opposite of short-sighted. You have no, I am short-sighted. You are far-sighted, so you don't have to be just old. Some people they cannot read close, so that's also a condition. So in that case, again, the image will be behind your eyes where there is no cones to record the image. So again, you need those glasses that are cheaper, right, to bring the image from here to there. Yes. Oh, yes. So far-sighted is when you can see far but not close. That means your eye, if you are young, that means your eye is too squeezed, right? It's the opposite than when you are short-sighted. Short-sighted is too flat, and then far-sighted it's too short, squeezed like this. So because it's squeezed, the image is formed there. You have to bring back the image at the right spot. Is that interesting? So that goes if you are in health. You never know what you're gonna end up doing. So nearsighted, the eye is too flat, so the image is here. So you need to wear those diverging lenses to bring the image back on the screen. And here is the opposite. If you are far-sighted, the image is here. So you need to wear a converging lens to bring back the image right here on the screen. So optics, you can have optical instruments. I think you have enough material that you are able to learn on your own. If you have to prepare for the MCAT, you have a microscope or telescope. So telescope, when you have something very, very far away, you're going to bring the image close to you. That's going to be very small. And then you have a magnifying glass to make it bigger. And here for microscope, you use two converging lenses, and the idea is to make it as big as possible. Yes.
Question. Wow. So,
Before the final. No, you cannot. I mean, I cannot add more than 8 points, maximum 10 points. So you can do 2. One video is one concept. But if you do 2 concepts, you can. But then it's hard to share. Like in Canvas, some people try to share a video with me, and then it's too big. So it's better to do 2 video, 2 concepts. Unless you can upload in YouTube and yeah. No, but you do whatever you want. One concept is between 3 and 5 points more. extra points. But no more than 2 concepts. You don't have to do 2 concepts. You can do 1 concept, 2 concepts, right?
The point is, how do we get that roll points?
All the points. You have to be very good. It's like 3 points, 3 to 5 points, depend how good it is.
For each.
For each concept, and it goes not to test 3 because test 3 is only 10%. It goes to the one of the tests. Doesn't matter. They all have the same weight, right? So okay, I have